Behind the cornea, we encounter that most distinctive feature of any eye, the iris. Named for the goddess of the rainbow, the iris is a rich panoply of color and texture. The colors are inherited, but because they don't affect how the eye works, the fine details can vary greatly. It's a mark of your identity, with patterns of lines and flecks that are as unique and personal as a fingerprint. Under the microscope, the iris is a work of modern art. White connective fibers attach the colored cells to tiny muscles which regulate the pupil. This may reflect your emotions. When you're in love, the dark pupil can become immense. But it also serves a more practical purpose. It gets larger when it's dark and smaller when we're exposed to bright light. Look through an enlarged pupil, and only part of the view is sharp. Turn up the light, and when the pupil shrinks, more of the picture now appears crisply in focus. The iris is surrounded by a clear, watery fluid. It flows all the time, replenished every 4 hours from glands behind the iris to nourish parts of the eye that have no direct blood supply. It flows forwards through the pupil to bathe the inside of the cornea, and behind the iris it washes over another bulging lens. Seen from inside the eye, looking outward, this slightly yellow second lens hangs by fibers like the spokes of a wheel, and the whole lens is encircled by a ring of muscle. And that muscle can squeeze and change its shape, fine-tuning its focus. The lens must become more curved and thicker if we're to see nearby objects in focus. Sadly, the design isn't perfect. As we get older, cells deep inside the lens begin to die off. Choked by dead, inflexible layers, the lens stiffens. Beyond the age of 45, most of us find it harder to focus on nearby objects.
So, how's it going? Have some tea.
Oh, thanks.
What's next?
I'm just putting in the shadows here to give some form.
What do you use for that?
Payne's grey and mauve.
Caroline's father is on the wrong side of 45.
Let me put some glasses on. Okay, so it's mauve, blue shade it says, right, okay, blue shade. I can see the picture better now too.
Still a young woman, Caroline has no difficulty focusing on her painting. Just as the liquid in the glass bends light, Caroline's fluid-filled eyes do the same. When she looks at an object, the light bends at the front of the eye, then passes through a natural clear jelly to focus on the retina. As she continues to work on the painting, she's totally unaware of a bizarre phenomenon. The optics of her eye have turned the image upside down on the retina. It's up to the brain to turn it back again, right side up. The retina covers 2/3 of the inside of the eyeball. Here at the back of the eyes, specialized cells soak up light and turn what we see into a stream of electrical signals. But when we examine a cross-section of the retina, it looks like someone made a crazy mistake with the circuits. The light has to travel through a dense wall of nerve cells before it strikes the detectors. These are the cells that make the difference between sight and blindness. You have more light receptors than there are people in the United States, all in the space of a couple of postage stamps. There are 2 kinds of receptors mixed together in the retina. Most are long, thin rod cells, which see well in dim light, but can detect images only in black and white. The stubby pointed cell is called a cone. It registers color, but works best in bright light. At the center of the retina, there's a dark region. In the middle of that, the microscope reveals a crater. This tiny pit is crammed exclusively with cones, and the wall of nerve cells that covers them is thinner. Here in the pit, light penetrates the retina more easily, and the cones at the bottom can detect the finest details of a scene. Without thinking about it, Caroline keeps the brush near the center of her vision, so its image falls on the cone-filled pit. So, her view is sharpest in the center and a little fuzzy round the edges. The sensitive center of the retina is easily damaged. The sun's intense focused energy could burn out those cells. Yet vision evolved to use light from the sun and to see it as all the colors of the rainbow. What we see is reflected light. From a lemon, only yellow light is reflected back to the cones of our eyes, so the fruit appears yellow. The human eye can distinguish thousands of colors, yet we have only 3 distinct kinds of cones to cover them all. One is sensitive to a whole range of colors, including red. A second kind centers on green, while the third favors blue. Just as 3 basic paints can be mixed to give an almost unlimited range of colors, nerve cells in the retina mix the signals from the 3 kinds of cones to give the illusion of other colors. It's only at the center of the retina that there are so many cones. Moving out towards the edge of the retina, the dim light detectors, the rods, take over. In this slice across them, the thick cones are far outnumbered by the colorblind rods. So the edge of our view is not just blurred, it has less color too. All of vision depends on chemical reactions inside the rods and cones. The most important of these occurs when light falls on a purple-colored molecule inside the cells, called visual purple. It absorbs the light's energy and bleaches out, similar to when light exposes film in a camera. The eye jumps from place to place, helping to keep the cells from getting overexposed. And unlike film, visual purple can be recycled and used again and again.